you are just a machine, an imitation of life. Can a robot write a symphony? Can a robot turn a canvas into a beautiful masterpiece?
Can you?
Well, it's a great pleasure and an honor for me to be here, and I'm using this wonderful modern technology here, which I hope works. So this is the title I've given to this talk, Why We Need New Physics to Understand the Conscious Mind. Now, this is about artificial intelligence and real intelligence, and it's also about why I don't think we have artificial intelligence. So I will come to that. But let me first say, well, a lot of things I'm not going to say, which are many features of consciousness, such as the feeling of pain or the color appreciation of the color red, or love, or intention, and all sorts of things which we attribute to conscious beings. I'm only going to concentrate on one thing, which is the word understanding. And the question, well, I relate three words that I don't know the meaning of. One of them is intelligence, one of them is consciousness, and another one is understanding. But coming from a mathematical background, I don't need to understand the words if I can say something about the connections between them. So I would say that in ordinary usage, the word intelligence requires understanding. And I would say in the normal usage, understanding requires some awareness. So I would say that for an entity to be intelligent in the ordinary usage of the word, it would have to be aware, it would have to be conscious. And I don't think that the devices that we know about are conscious, but I'm not directly addressing that argument. What I will more directly address is the issue of consciousness. Because consciousness is something I think we can say, what I do directly address is the issue of understanding, because I believe that understanding is something we can say something quite objective about. And I'll start with a chess position which I made up recently. We know that there are chess players, computer-controlled algorithms. These are devices which will play chess better than any human being. So you must say that surely these chess programs understand chess. Well, the most effective of these chess programs is called Fritz. And this position was given to Fritz. It's a position I made up deliberately because if you notice the black pieces, there are many more black pieces of significance. There's two extra. You might worry, you might think that this position is not a legal position because there are three black bishops all on the same color. But it is a legal position because two of them came from pawns, which came, the pawn that was missing here and came onto that white square and became a bishop, and the other one was one down here which went to that square and made bishop. There's nothing illegal about the position. It's a stupid position. It would never occur in an actual game, which is one of the reasons that Fritz has no idea how to play this position. Because to a human being who knows very much about chess, you will see the knight is trapped, it can't do anything. The bishops can move around a little bit. The king can't get out. And so these pieces are all trapped behind this barrier. And the pawns here, the free bishop, black bishop, can't do anything. It's on the wrong color to get these white ones. It has to make sure it keeps guarding that one. And then there is no way it can lose. There's no way it can win. It's an obvious draw. However, you give this position to Fritz, it says it's a win for black. And that, I should say, is its downfall. because it plays the game for a while, it makes a completely stupid move and loses the game, which is what I expected. It loses the game because by some kind of count, I don't know exactly what they do, it thinks is the wrong word, it decides that it is a win for black because of just counting pieces and counting up maybe 30 moves ahead, and it doesn't make any difference. It's still got more pieces. And so it concludes that it is a win for black. And since it's of that opinion, when it comes up to close to the 30-move rule, which says if a piece has not been taken or a pawn has not moved, then it's a draw. And since it considers that the game is a win for black, a draw is a disaster. So therefore, it either sacrifices the bishop, or it takes the bishop away from this line here, and the king can take this pawn, and then the pawns march up, and you can make 3 queens, completely overwhelming the position, and it is a win for white. Eventually, Fritz agrees it is a win for white. But you can see it has no understanding whatsoever of the game of chess, because it would appreciate any player who knows very much about chess at all will see this as a draw, and it's very stupid to give up the bishop or to release this pawn so it can make a queen. Okay, that's only a special case. I just use that as a demonstration to show that understanding, despite the training that these programs have and so on, it doesn't say that they understand the game, and I don't think they do. Now, the thing about chess, of course, is it's a finite game, so you might run out of positions like this. I'm sure that there will be people now, as I speak, who are trying to program Fritz so that given positions like that, it will not make that stupid move. It's not so easy, but, I talked to somebody and said, well, I can make my computer do that. Well, of course they can, because Fritz isn't deciding how to change the program. It's a human being who understands what's going on, who understands the program that underlies how Fritz behaves. So the understanding is on the part of a human being, not on Fritz. But nevertheless, chess is a finite game, so you might worry that, okay, it can be completely analyzed, and then mistakes like that will not be made. So we have to concentrate on the infinite. Now, you might say, some people think that infinite is something you can't understand, you can't contemplate. But nevertheless, it's not true. We can understand the infinite, any one of us could. If you take 2 even numbers and add them together, you get another even number. Now, that is a statement about all numbers, all whole numbers. We can do that, but that's a statement about an infinite number of things. There's no problem about talking about an infinite number of things and understanding an infinite number of things. Sometimes it can be very difficult. Sometimes it can be easy. But what I claim is that the machines don't have this ability. And there are theorems which more or less tell you that. Let me give you a famous theorem. I'm going to give you the Gödel theorem. No, I won't do that first. Wait a minute. First of all, let's just say a way that we learn about the infinite, at school, we learn mathematical induction. Now, this is one way you can understand the infinite. When I'm talking about natural numbers. When I say a natural number, I mean whole numbers which are not negative. 0, 1, 2, 3, 4, etc. So those are the natural numbers. Now, suppose you have a proposition which depends on a natural number. Now, if you prove that this proposition is true for 0, or if you can see it's true for 0, and you can see if it's true for n, then it's true for n plus 1, then you know it's true for all numbers. So you just establish 2 things, and those 2 things tell you it's true for all numbers. So this is a way you can establish things that are true for all numbers. But I'm going to say something about the limitations of that. The first thing is a very general statement, which is due to Gödel, but I shall give it in the form due to Turing, which is a very nice way of saying it. That is to say, if you're given any set of rules, I'm calling the rules R, any set of rules which could be checked. You see, you have a set of states, you have a set of propositions, 1, 2, 3, 4, like that, each of which follows from the one before by the rules R. And I'm just insisting that a computer could check whether the rules are correctly carried out. So that's all I require. Now, let us say these rules are meant to be ways of proving theorems about numbers. It could be Fermat's last theorem, which was proved by Andrew Wiles, or it could be the Goldbach conjecture, which says every even number greater than 2 is the sum of two prime numbers. Still not known whether that's true. But that's the kind of proposition I'm talking about. Things about an infinite number of things. Now, the rules have to be such that if you follow the rules correctly, and it says you feed the rules a particular statement like that, and the rules chug away, and if they can obtain, yes, that's true, okay, then you have to believe, yes, it is true. It might say, no, that's false, okay, or it might not say anything. It might just go on and on and on and on forever. Now, let's suppose that you believe that the rules never say a falsehood, like 2 + 2 = 3. Let's assume that it never gives you something which is blatantly false. But that it only gives you things that are true. Well, what Gödel shows, that you can construct a particular statement. You look at the rules and you say, there's a way of constructing a particular statement about numbers, like the Fermat theorem, like the Goldbach conjecture, a very specific statement. And you can see from the way it's constructed that, first of all, it's true. And secondly, it's not obtainable by means of the rules. Now, this is a very remarkable thing. When I first heard this, I was stunned, because what it tells you is not that these things are not provable, because the very thing that you construct is something that you know it's true. But you know it's true only because you trust the rules. So that means if you believe that the rules only give you truths, then that belief transcends the rules themselves. Very remarkable thing. It means that the understanding of why the rules work tells you something that the rules cannot achieve. It tells you that the rules cannot achieve something, but nevertheless that is true. You can see it's true by the way it's constructed if you trust the rules. Now, when I first heard that, I was amazed, because it seems to tell us that there is something in our understanding. You don't have to invent this. You don't have to be Gödel. You don't have to be Turing. You don't have to have the inspiration to see why this is true. All you have to do is follow it. You follow the reasoning, and you can see by following the reasoning that the statement that comes up, the G of R, is true if you trust the rules. So that the trust in the rules, or the belief in the rules, or the understanding of why the rules work gives you something that the rules do not give you. And that tells you that understanding, it tells me that understanding is something which is not achieved by rules. Now, there is something more about that which I'll come to in a minute, but let me give you some example of something that computers can't do. Now, it's nice to see these examples. There are many such examples, but this is a very nice one because it's very easy to understand. Suppose you are given things like this, which are made out of squares, all the same size, and they are glued together along their edges. And you can make various shapes in the plane. Here I have some examples of shapes. They're called polyominoes. Now, it may be that some of these shapes you can cover the entire Euclidean plane just using that shape. Here's an example. There's another example. You might have a shape like this, which you cannot. You always find a gap. This does not work by itself. This shape does not work by itself. There's always a gap. But if you have the two together, yes, they will cover the plane. Here's another one. A little bit difficult to see why, but this will cover the plane. Now, it's a mathematical theorem that there is no computer algorithm which will tell you yes or no whether a finite set of polyominoes will tile the plane. Now, that's very remarkable. But let me give you an example. Here's an example. I made this one up myself, but it shows you the difficulty. These three shapes will tile the plane. But if you look at that pattern and they let you stare at it for a while, can you see the pattern by why it's constructed? A very well-known mathematician asked me, he said, I could not see how this was constructed. How on earth did you do it? Is there an algorithm? Well, there is an algorithm to see how to do this. What you do is you look up in my collected works and you find there is one paper where I tell you how to do it. And that's how you can find how to do this. But that's not an algorithm of the kind I mean. You're not allowed to look up my papers. That's cheating. But nevertheless, there is a way of covering the entire plane with these shapes. And I don't think it's very easy to see that, and I don't know of any computer program that would do that. I know of a computer program that I could see probably how you could do it by talking to somebody who knows how to program properly. It would be very difficult, but nevertheless, it can be done. So I just give you that as an example of something which is not computable. Yet it's possible by using the right kind of reasoning. Maybe, I don't know whether it's true in all cases, but it seems to be possible that you can tell with insight, at least in many cases, that these things can be done, but there is no general algorithm for that. You might ask, how do human beings, how they're able to decide this kind of thing? And also, let me give you another example which is related to this. This is an example which was put forward in 1945 by a mathematician called Goodstein, and I want to try and tell you what it is. This, you take any natural number, and here I've got an example of 1,077. Now, the first step is to write this number in binary, which I've done here, in zeros and ones. What does that mean? Well, each of these ones represents a power of 2, 2 times 2 times 2 times 2, a certain number of times. And I add a distinct set. The ones represent a distinct set of powers of 2. So that you are representing this number as a sum of different powers of 2. And that's what the binary notation means. Now, you might argue, well, since we've represented these numbers in binary, what about the exponents? Okay, well, you see some exponents up here. They're not written in binary, but you could write them in binary too. So you have these numbers here. And then you can go again, and you may find lots and lots of, you may have go several steps up, but you can always finish, and you've written your number in terms of sums of powers of 2. Okay, now I'm going to give you two operations. One operation is A, and what A says is look at all the 2's and replace them with 3's. Okay, well-defined operation. The number gets much, much bigger. Never mind. That's operation A. What's operation B? Subtract 1. Okay. It comes down just a little bit. Okay. Operation A, replace all the 3's by 4's, subtract 1. The subtract 1 sometimes is a little trickier here because you don't have a nice 1 at the end. So you have to, it's like subtracting 1 from 1,000 and you get 999. So you've got to make sure that when there isn't a nice handy 1 at the end, you've got to replace it by the... Notice that the base is 4, but you have 3's here, which are the coefficients, and they're always smaller than 4. So then you replace that by 5, subtract 1. Now this is an amazing example of a hare and a tortoise. The tortoise always wins. Now that's remarkable. You see, what happens with these numbers? Well, the first one is about, whatever the number is, well, it's 1,077. The next number is about 10 to the power 40. The next one is about 10 to the, they get bigger and bigger and bigger and bigger, and finally end up with 0. It's very extraordinary, because the numbers get huger and huger and huger and huger, but subtracting 1, that's the tortoise, always wins. Now this is remarkable, not just because it's true, but because it was proved by Paris and Kirby that you cannot prove it using ordinary mathematical induction. So that was the one which I probably now can't find. Here we go. You cannot prove it this way. And it's an example of a Gödel theorem. Now, I'm not going to ask you to try and prove it. If you know the right mathematics, it's not hard. But it's not that, you have to use what's called transfinite induction. But it always comes to 0. And I would suggest, if you want to try, go home and try it with 3. That is to say 2 plus 1. 2 to the 1 plus 1. That's easy, comes down quite quickly. Try it with 4. I would not recommend that you put it on your laptop. I would not recommend that you use your mainframe computer. I would not recommend that you use any computer. I would suggest you use a pencil and paper. And you can probably convince yourself that it will eventually come down to 0. But if you put that on any computer which exists today in the world or is conceivable in the world, it will never do it. The number gets so huge, it's remarkable, even with 4. 2 to the 2. Then the first A goes through 3 to the 3, and then you subtract 1. Doesn't look very big, but the number gets huger and huger and huger. But we can understand that. It's not so obvious, but nevertheless, especially with 4, I think most people could convince themselves that the number will come down eventually. How do we know that? How is it? Some people would say, well, we have an algorithm in our heads which is so complicated that we cannot apply the Gödel theorem, and that's why it doesn't work, because it's too complicated. I don't believe that. Why don't I believe that? All sorts of reasons. But one reason I don't believe it is because how did our understanding come about? Well, by natural selection. That I do believe. But the natural selection it's not very good at making mathematicians, I think, if it's just algorithms. Well, I have this cartoon, which I've used before. See, here we have our distant ancestors, and they're doing all sorts of useful things, like building shelters, they are growing crops, they're domesticating animals, doing all sorts of things using their understandings, building mammoth traps. Here's a mammoth trap. Understanding in a general way, yes, indeed, was very important. But understanding mathematics, here is a mathematician. Let's suppose he has an algorithm in his head that's been selected for, has it? He's about to be eaten by the saber-toothed tiger. You see, I'm trying to say that being a mathematician is not really a selective advantage. I don't think it was then. I think it probably is not now either. So how did this understanding, we can do this Goodstein, well, with the number 4, we can do the Goodstein theorem, whereas no computer can do that. How is it we have that understanding? Well, it's a general quality of understanding which is not an algorithm. It's not of a very complicated algorithm. So that's all I'm trying to say. This cartoon is meant to show that, okay, what was a selective advantage was the general quality of being able to understand, and that this was not a computational quality. So that is the message which I'm trying to make. Now, you see, I formed a view something like that when I was a graduate student at school, because I'd gone to a course by a man, when I was at university in Cambridge, I went to a course on mathematical logic, and I learned about the Gödel thing, and I say I was amazed by that. But then I thought, okay, if our heads are not governed by algorithms, and you've got these neurons, and it looks like a computer in some sort of way, what could it be? And sure, I was trying to do physics. I was trying to understand how the physical world operates, and I could understand, well, later certainly, that you can put very complicated things. I mean, we hear about these black holes which produce these signals, and LIGO says, oh, there's been a black hole over there. So they swallowed each other up, and they produced these very complicated signals. We know that's a black hole. Why do we know that? Because of people who did very complicated calculations to work out the exact shape of the signal, which indicates that's a pair of black holes coming together. Computation. Now, that computation can simulate the action of Einstein's theory to a tremendous precision. Okay, what can we be doing in our heads? Well, maybe it's not relativity, maybe it's ordinary Newtonian physics. Well, you can do very, very good computations. What about quantum mechanics? Well, that's an interesting question, because you can follow the Schrödinger equation. Again, can be quite difficult, but again, it's purely computational. But when I was also a graduate student, I went to a course given by the great physicist Paul Dirac. And in the very first lecture, he had a piece of chalk which he put into 2 places. He was talking about the superposition principle in quantum mechanics, which says if a thing is here, it could be here, then you have a state where it's here and here at the same time, with certain complex number weighting functions. So it can be in 2 places at once. And then he'd take a piece of chalk, and he broke it and put it in 2 places. And he said this chalk, and then he explained why a piece of chalk could not be in 2 places at once. And my mind, unfortunately, had wandered over, and then, what? And he went on to the next thing. And I never heard the explanation. So I've worried about it ever since. And he said something vaguely about energy, but I didn't know what that was. So from then on, I've worried and worried about how on earth the piece of chalk could not be in a superposition. But the rules, quantum mechanics said, yeah, you could make a piece of chalk within 2 places at once. Or Schrödinger said you could have a cat which is dead and alive at the same time. I should point out, he pointed out this example just to show why his own equation is not the whole story. There must be something else. He was deliberately showing the absurdity in his own equation. I think that's very remarkable. Now, I'm going to tell you about quantum mechanics, but in doing this, I'm going to use just a cartoon. Here is quantum mechanics. Now, you see, what's that picture doing? Well, you see, I was invited by the Hans Christian Andersen Society to give a lecture in Odense, or however you pronounce it, in Denmark. And I thought, why on earth have they asked me to honor Hans Christian Andersen? But, oh, yes. Well, I wrote a book called The Emperor's New Mind, which is a play on the Emperor's New Clothes, which is the Hans Christian Andersen story. But I thought, well, I must think of another one. Well, I can't use that one again. I thought of The Little Mermaid. And I had the mermaid being dead and alive at the same time. I won't go into all that, but it was part of the story. But this picture is part of the lecture I gave. And it illustrates quantum mechanics. How can it illustrate quantum mechanics? Well, the picture is really two things. Because at the bottom, well, the top is the classical world. You see separated things, these buildings and people around, and they have locations here and here and here. And the bottom is the crazy-looking quantum world, which is all entangled up in complicated ways, and that's all under the sea. So that was my picture of quantum and the classical world. And what is the mermaid doing? Well, the mermaid is magic, and she represents here how to get from one world to the other. She is the magic of the reduction of the state or the collapse of the wave function. It's what you have to do in quantum mechanics. You use Schrodinger's equation up to a point, and then you say, well, no, this is getting too wild. Dead cats and live cats. So you sometimes say, well, you look in the box the cat was, and you see, your consciousness gets involved with that, and you somehow make the cat be dead or alive instead of being a superposition. I never believed that. It seems to be there's something out there in the physics of the world which is making that choice. And that is the magic of the collapse of the wave function or the reduction of the quantum state, which is what the mermaid is doing. So this is how the classical physics comes out of the quantum world. It does not come out of it in the way we understand quantum mechanics now. So I gradually began to think that this thing I did not understand in Dirac's lecture is a really profound something missing in the physics. And it's the only thing I could see that you could not put on a computer. So it seemed to me that must be what we take advantage of, what consciousness is. And well, I should say, maybe I should just give you an example first. After a lot of thinking, I came up with a formula. I should say there's a Hungarian physicist who thought of the same formula earlier than I did. But let's suppose you have a body, and you try to put it in two positions at once, and you want to know how long that will last. And I would say it will become one or the other in a certain length of time, which depends on an energy, but it's not exactly, I don't know what Dirac was saying, but what you do is you look at the energy in this and the energy in that, or the mass distribution in one and the mass, and you subtract one from the other. So I'd put it like this, negative, you see. Subtract one from the other, and you work out what's called the gravitational self-energy of that, and that's the thing I called EG, and EG is an uncertainty, and the lifetime is reciprocal of that. Let's not bother to go into that. But I'm just saying that you worry about the densities and all that. That just makes it more complicated. But there is a formula that one can suggest, and I believe that this formula is very possibly true. Experiments have not yet established whether it's true or not, but it will tell you, the piece of chalk of Dirac, that when it would become over here, when it would become, or over here. It doesn't tell you which it does, but it will tell you when it becomes one or the other. And the idea is that that process is something which is not computable. In fact, it's something which is a bit like what free will might be, because according to current physics, it's making its own decision. Somehow, does it decide to be here or here? Somehow it decides. I don't know what that means. But my colleague Stuart Hameroff, and I'll say a little bit more about him, we have this theory where we try to say that conscious decisions are processes like that, that somehow the decision has to be made between this or that, and that decision is not determined. I'm about to finish, so I'll just give you some pictures. You see, when I had these ideas when I wrote The Emperor's New Mind, thank you very much, when I wrote The Emperor's New Mind, but I had no idea where in the brain there could be anything like that happening. I knew about, I started reading all sorts of things about nerve transmission and this and that, and I thought, no, that can't be, no, that can't be it. And I thought, optimistically, by the end of the book, I would know the answer. That was stupid of me. At the end of the book, I didn't know the answer. But still, I didn't stop me writing the book, and it was published, and I hoped that I would find some young people who would be inspired by the physics in the book. Mainly it was old people who were retired who wrote to me, and those were the people with enough time to read my book, I suppose. But anyway, I did get a letter from Stuart Hameroff, whose job is to put people to sleep in a reversible way. He is an anesthesiologist, and this is his job. But unlike many of his colleagues, he wants to know what he's really doing. Of course, he wants to put people to sleep so that they are not put in danger and that they can be woken up again without having suffered from the consequences, and maybe the operation that has been performed has been successful because the person has been not conscious. And Stuart was very interested in what he's actually doing and came up with the idea that what the general anesthetics affect are not the neurons directly, but these things called microtubules. And when I heard about that, I thought that's much more likely, because these are long, thin, nanoscale tubes which seem to preserve coherence. And that's the sort of thing we want. So we developed a theory between us. We still don't know really what's going on, but the microtubules are a key part of this. And the claim is, well, this is many neurons acting together, and this is just to show the experiments on microtubules, which seem to indicate something quantum mechanical is going on inside these little tubes. And they influence the synapse strengths, and that is what they're a deeper level than synapses and neurons. But what makes the neuron structure do what you want is controlled at a deeper level, and the controlling of that has to do with this new physics. We don't know it yet, but I claim it's something like the process I've just been talking about. So there's lots of exciting things to find out here. Is this true? There is some good evidence, I believe, recent evidence, that the way that general anesthetics work is that they do act on microtubules. The microtubules seem to be a key thing in way general anesthetics act. So I think that's promising. But exactly what's going on is something for the future, and I think it's really interesting. But this point of view suggests that there is something very different in conscious action. What the terminology we've come up with is, we'd say, proto-conscious. So that each time the world makes a decision, it's this thing in the mermaid, you see, where the arrow comes and the mermaid creates something, comes from the quantum world to the classical world. And each time that happens, it's associated with an element of proto-consciousness. It's not real consciousness yet, because there's no purpose together. It's there's no mechanism which makes it have meaning. But the idea is that those are the building blocks out of which consciousness is constructed. And that when we understand that, maybe we can make a device which is conscious, but the computers of today are not conscious, and as long as they remain computers, they will remain unconscious. This says that they will not take over the world. I don't think that's the danger. I think there are dangers. There are many dangers. I haven't talked about that, and I don't have any time to talk about that, so let's not. I leave that to others to talk about. Thank you very much.